Hello friends, welcome to another video. In this video, we are going to implement the deep residual unit architecture in the PyTorch framework. To learn more about it, make sure that you watch the complete video and subscribe the channel. The deep residual unit basically consists of the unit architecture with a deep residual network inside it. So let's see the diagrams. So here in figure 1a part, you can see the plain neural unit using the unit architecture, which is replaced by this residual unit with identity mapping. Okay. In the figure 2, you can see the complete block diagram of the res unit architecture. And we're going to use this block diagram to implement the res unit in the PyTorch framework. So if you are new to the PyTorch, make sure that you subscribe the channel because I'm going to upload more videos related to PyTorch framework. So next, go to the paper, and in the table 1 we can see the network structure of the res unit architecture. This table is also really helpful in the implementation, as we can especially see the shapes and the stride values, the number of the filter size and the number of filter. Okay, so these things are really helpful. So let's start the implementation in the PyTorch framework. So first we are going to import the libraries. So here we have imported the torch. Okay, so let's start building a class called build a res unit. Okay, so this M should be capital. Okay, so this is till there. So now we will start with the first encoder 1. Now we'll go to the diagram and see things again. So if we go to the so see the first encoder, so this is the first encoder. So let's start with the convolution. If we take the input image and then followed by BestNormalization Reload, again a convolution, and then a addition with the identity mapping. So this identity mapping is basically a one by one convolution, because if you're going to add the input has basically 3 channels, and the convolution the convolution layer would give like 64 as the number of channels. So you cannot add two feature with like one has 3 channels and another has 64 channels. So you need, so we pass this input image with a one by one convolution and make sure that they have same number of channels, and then we perform addition. So you will get this when I start programming it. Okay, so let's start programming it. So we first start with a convolution layer. Okay, so we're going to call it C11. It has 3 input channels would be 3 and the output channel would be 64. So if you go to this table 1, you can see the number of channels are 64. They start with 64, then go to 512, and then again reduce by a factor of 2, and again end with 64. Okay, so after convolution, this is BestNormalization and then reload. So if you look at this complete architecture, the block diagram, you can see the BestNormalization and reload are repeating everywhere. So what we can do, we can first build a class called BestNormalization and reload. Okay, so it would be much easier for us to write the code because we won't have to repeat everything. Okay, so this is the name of the class, bestnorm_reload. It's a child class of the NN module class. Okay, next we have the constructor, the init line, which takes the number of input feature in the input feature map. Then we add 2 layers inside it. First is BestNormalization and the second is the reload activation function. Okay, then we say forward function of the class itself, which take the input feature map. Okay, next, so we're going to pass this input first through the BestNormalization layer, and the output will be written in this x variable. Then we're going to add the reload, the BestNormalization followed by reload, and we're going to return the output of the reload. Okay, so now what we're going to do, we're going to use this BestNorm here. So we're going to call this BestNorm as BR1. BR basically refer to BestNormalization and reload. Here the number of input channel would be 64 as the convolution layer C11 output a feature map with number of filters as 64. Okay, next again it is followed by another convolution layer. we're gonna call it C112. Here the input channel would be 64 and output also be 64. Okay, next comes the shortcut connection. So shortcut connection basically identity mapping. Okay, it's a one by one convolution. So we're gonna call it C13, and it takes 3 number of channel because it would take input image as the input feature and output would be 64. Here the kernel size would be 1, so padding equals to 0. Okay, so this is done. Now we move the forward part, the forward function. Okay, so here let's write encoder 1. Okay, so we're going to say x is equals to self.c11, that is first convolution layer, giving it inputs as the input, that is followed by the br1. Next again the second convolution layer called c12, input is x. Now come the shortcut, the identity mapping, which is basically c13, the convolution layer c13, giving the inputs as the input. Then we add these two things, the output, the shortcut connection, and the output of the second convolution layer. So we're going to say skip1 is equals to x plus s, and we call it skip1 because if you look at the diagram, you can see the output of the addition act as the output for the next block, next encoder block, and as a skip connection for the last decoder. Okay, so that's why we call it skip1, because we need to remember and save this value. Okay, so if you look at the diagram again, so next two block are basically the residual, they are same, so we can create a class for them also called residual block. Okay, let's create another class called residual block. Okay, it should be class, not a function. It should be a child class of nn.module. First is input channels and then output number of channels. Okay, okay, so here we're going to define, first we're going to define our convolution layer. Okay, so we're going to say first it is followed by the best normalization the reload. We're going to call it b1 best norm reload, and we provided the number of input channel, then it is followed by the convolution layer, we call it c1. Number of channel, input channel would be inc, output would be out c, kernel size will be 3, padding is 1, and here comes the stride, because this network don't use polling, it uses stride. So here we can, let's input the stride here as parameter argument. Stride, we can say default is 1, so we're going to provide stride. I will just show you one more thing from the paper. So if we go to the this table, so here you can see this is the first level 1, means encoder 1. Okay, here the stride are 111. If you go to the level 2 and level 3 and level 4, you can see the strided 2 for the first convolution layer. So they don't use pooling operation, they use strided convolution to reduce the spatial dimension of the previous feature map. So the residual block would use a stride of 2. By default we provided 1 because this residual block will also be used in the decoder. So we manually tune this value 2 for the encoder block, and it will remain 1 for the decoder block. Okay, so now let's continue with the more layers. More layer basically a copy of this only with a few changes. So b1 becomes b2, and number of input channel would become out c. Here it would also change, and the convolution layer would be called as c2. Here the stride would remain 1. If you see the paper, first is the stride value is 2, second is 1. Okay, so these are the convolution layer. Next comes the shortcut connection or identity mapping. So here the convolution layer is called S, and it has the number of input channel as inc, output is out c, the kernel size is 1, so padding is 0, and the stride is the default value provided by the user. is the value provided by the user. Next we will follow the forward function and see what happens there. Here we just define the layers. Main operation just happens in the forward function. Okay, you want to say x is equals to b1 inputs x, then it is followed by the c1, then the b2, and at last it is followed by the c2 convolution layer. Okay, so this is the convolution. Now there comes the shortcut. You can say s self dot s, we can say, because s is the name for the convolution layer. Here you can say self dot s, and here we provide inputs as the input to this convolution layer. Next we need to add, and we're going to call it skip. And you know why we call it skip? So comment below why do we call this variable as skip. Why do we save the addition in a variable named skip, and we're going to return skip. Okay, so this is the residual block, and it is used as the encoder 2 and 3. Okay, so we need to define the residual block 2 and 3. So we're going to call them self.r2 residual block. The input would be 64 and it doubles by a factor of 2, and it became 128. Stride value would be 2. Same thing we need to define, just changing some variables in it. Stride would remain to 2, and the name would change to r from r2 to r3. Then input filter would be 128 and output filter would be 256. Okay, so encoder is defined. Now we're gonna run these layers in the forward function, and we're gonna say skip 2 is equals to self.r2, and the input would be skip 1. Same for the skip 3, that is residual layer 3 r3. Input would be skip 2, that is output of the second encoder block. Okay, so this is done. Now let's print the shape of the 3, and we're gonna check if there's any issue till now here. Okay, so first we're going to create a random tensor. Inputs is equals to torch dot ran n. So here in PyTorch, it is first followed by the batch size, then the number of channel, and then height and width. But if you are new to it, this may sound unusual to it. If you came from the TensorFlow background, then in TensorFlow it's like for the batch size, then followed by height and width, and at last comes the number of channel. But in case of PyTorch, it is followed first, it is followed by the batch size, then the number of channels. So that's how things change in PyTorch. So we're going to say build res unit. Okay, and then we're going to say model. Okay, it should be like model equals to build unit, and we're going to call the model object and provide it's the inputs. Now here, okay, let's activate our environment first. Oh, it should be PyTorch, not TensorFlow. I have separate environment for both the PyTorch and the TensorFlow because it's easy to manage things like that. The main system library does not affect. We're gonna say res unit. Okay, so issue. There's some issue here, and the init call in the we can say build res unit first, and then this line number 44. Okay, so let's check the line number 44 in this best norm reload. Okay, I knew what's the issue is. You can call the super function here because it's a child class of another class. Okay, now I assume everything would run fine. Okay, so you can see everything is running fine. So we have batch size is 4, and number of filters changed to 256, and height and width became 64 by 64. So now we come to the bridge part. Okay, so here's the bridge. So if you look at this diagram, everywhere they have used residual learning and this identity mapping, but why they haven't just draw this arrow, the identity mapping arrow to the addition, and they have shown addition block here. So this means that some function is coming from the top and adding here. I don't know it's an issue or anything. Just comment below what do you feel. They just made a mistake in this paper. I don't know. So let's build the bridge. Okay, so we're gonna call it the bridge. It's also a residual block, or we can say bottleneck. Both are same. We're gonna say bridge as B or R4. Let's call it R4. Residual block. Input would be 256 and the output number of channel would be 512 and stride would be 2. Okay, so this is the bridge. Next, this is followed by the decoder. Okay, so we're gonna call B is equals to self dot R4, and input would be output of the third encoder block, that is skip 3. Okay, next comes the decoder. Okay, so we need to create a class called the decoder. Okay, let's create a module. So let's create a class called decoder block, and then we have the init line. It takes which have the argument the input channels and the output channels for the convolution layers. Okay, then we have this line super, because we are using a different class as the parent class. Okay, let's define the mode structure. So if you remember the decoder block, it take two input, first the previous layer feature map and second the skip connection. Now we'll look at the diagram. So you can see the previous feature map goes through the upsampling layer first. Okay, so here in upsampling it doubles in size. If the output size of this and the height and width of this feature map, this arrow is like 64 by 64, it passes through this upsampling layer and it became 128 by 128. After that, it is concatenated with the skip connection. So you can see the first decoder block take the skip connection as the output of the third encoder block as a skip connection. Then it is followed by the residual network simply. So let's do this. First is the upsampling block. First is take the scale factor as 2, because we need to double the height and width. So scale factor is 2, mode is bilinear. So here we are doing a bilinear upsampling. Align corner true. Okay, so let's do this. We can call x self dot upsample, giving it the inputs as the input. Next, it is followed by the concatenation. Before using concatenation, make sure the output of the upsampling block and the skip connection have same shape, that is height and width. Number of channel can be different. So let's do this. Let's create a decoder block here called D1. Okay, so it takes 512 as the input channel and 256 as the output channel. Okay, now we call D1 here. So we're going to say D1 equals to self dot D1. Input would be B, the output of the bridge, and skip connection would be the skip 3, that is output of the third encoder block. Okay, so let's run it. Check for the shape. Okay, so this is the output of the upsample block and this is skip connection shape. So here you can see the height and width are 64 by 64 in both the feature map, but number of channel are 512 and 256. That's not an issue. These height and width should remain the same. That's the major issue. So let's concatenate them. X equals to source dot cat, and inside there's a list where we use give it x and the skip connection, and we are join them on the axis 1. Okay, that's good. Okay, next it follows the residual block. So residual block first take the input number of channel. So input number of channel would be 512 plus 256. I think 768 it would be. So we're gonna say here self dot r residual block. So it would be, if you see, this is the first decoder block, and in the features are 512 and 256. And if you look at the input and output number of channel, it is 512 and 256. So we need to add them here in the rest block. The input number of channel would be inc plus outc, and output channel would be outc. Okay, so that's how it works. And here we say x equals to self dot r. Input is x, the concatenated feature map. So we're going to return x here, the output of the residual block, and it is followed by the 3 more, and so one is already defined and 2 more need to be defined. So this is d2 decoder block. So decoder block input number of channels will be 256 and the output would be 128, and is followed by the third decoder block. Decoder block input number of channel 128 and output number of channel would be 64. Okay, so now let's move to the forward function. Let's say d2 equals to self dot d2, and input would be the output of the first decoder block, and skip connection would be s2. Third decoder block d3, self dot d3, input would be d2, output of the second decoder block, and first skip connection first. So now we have completed the decoder block. So I assume shape of the d3 would be 256 by 256, that is same as the input shape. So let's run it. Okay, so you can see the number of filters are 64 and height and width is 256 by 256. So last it is followed by convolution layer and a sigmoid. So with this sigmoid we can assume the number of channel is 1. You can change it accordingly. The number of classes is not compulsory, you have to use 1. It's up to you how many classes you are working with. Output. So output is basically a 1 by 1 convolution layer. Number of channel input channel is 64, output is 1, kernel size is 1, and padding equals to 0, and then last it is followed by the sigmoid. It's up to you. If you don't want to apply the any activation function to the output, you can take the row value, or you can call this row value as logits. Basically you can take the logits and then apply the activation, because some loss function take logits and some take like the logits passes through the activation function. So it's up to you, it's the choice, it's not compulsory. So the input for this output would be d3, and last it is followed by the sigmoid. And we are going to return output. So the architecture is basically completed. So let's pin the shape of y, because shape is important. Okay, wait. Okay, so you can see the output number of channel here is the 1, and height is 256 by 256, same height and width the same. So the architecture is basically complete, the implementation is complete. Okay, I hope I was able to give you some information through this video, and if I did, make sure that you like the video. So this is the implementation part, and in some of the few videos I would use both the unit architecture implemented in PyTorch and this the resunet one, and make more training videos like training on a segmentation dataset for both the single class and the multi class. Okay, so for this video I think this is enough, and if you still have any query then please comment below and subscribe the channel and click the bell icon. So till then, thank you.